In these videos, we're going to show you the steps to process and interpret the spectra of stars that you've captured. We'll be using a program named RSpec, which stands for Real-Time Spectroscopy. See the PDF lab notes for where you can download a copy of the software. The lab notes also contain a checklist that lists step by step how we'll process your spectra. This is the first screen you see when you start RSpec. On the left side over here is a live video view. So there's my hand, and over here, this is a glass tube lamp filled with hydrogen. Let's turn it on. So there, you can see the tube lit up, and to the right, you can see its spectrum. You know, when you captured your first spectra with a telescope, there was a small diffraction grating on the camera. It split the starlight like a prism would. In this first video, rather than a diffraction grating in a telescope, we're using a lab spectrometer called RSpec Explorer. It also has a built-in diffraction grating to split the light. In fact, we're hoping that your teacher or professor had one of these RSpec Explorers. Maybe he or she demonstrated some of the cool things you can see right there in your classroom without a telescope. Or maybe you've already done a lab with it. Here's a diagram that shows how a spectrometer works. At the top, this is the source of light. It could be a star in the sky, or it could be a gas tube like the one we're seeing here. The light goes through the grating, which spreads it out according to the color. And finally, the spectrum falls on our camera sensor, which is what we're seeing here in this RSpec window. In our gas tube spectrum, you can see a dim rainbow in the background. But the important part of the spectrum are these bright vertical lines called emission lines. So where do these color lines come from? Well, we're not going to get into a lot of technical detail, but let's spend just a moment on this. Here's a model of the hydrogen atom. The dashed lines in this Bohr model are the so-called orbitals that the electrons circle around in. When an electron jumps down from an outer orbital to an inner orbital, it gives off light. And we can see that the color of the light emitted depends on which orbitals the electron is jumping between. So, the reason that these emission lines from the gas tube are these specific colors is that they're produced by electrons dropping down between different orbitals. So let's analyze this spectrum. The first thing we do is tell RSpec the region that we want to analyze. I'm going to drag these orange lines so that the spectrum is between them, like this. So now, see that graph on the right? That's called a spectrum profile. It's an intensity graph. RSpec has converted the region between the orange lines into this graph. How did it do it? Well, RSpec looked at each column in the image one by one between the orange lines and added up all the pixel intensities in that column. And then it plotted the result over here on the right. So this high peak is from the gas tube itself. And these peaks here are from the bright vertical lines in the spectrum. For example, this red peak on the graph is from this red emission line in the spectrum. And this purple line in the graph is from the purple line on the left. And notice that the x-axis is labeled in angstroms for wavelength. When I hover my mouse over peaks on the profile graph, a call out appears showing the x-axis wavelength. For example, this peak is at 4085 angstroms. So this is how we convert the qualitative spectrum on the left into scientific data that we can study. And this is how you're going to study the star spectra that you captured. Now, before we move on to the spectra of stars, let's step back just for a moment. Take a look at this. It's the periodic table of elements. In the standard periodic table that you've seen before, each box contains the properties of the element, like atomic number and weight. But the boxes in this version of the periodic table contain a sample of the element's emission spectra. Let's zoom in on this corner of the table. Notice that each element has a different set of spectrum lines. For example, the spectrum of lithium here is different than that of hydrogen. And yes, that's the same element lithium that's in the battery in your cell phone. Here's the key idea. Each element has a unique spectrum, just like a fingerprint. And that means we can use a spectrum to identify the materials involved. I'm going to slide the periodic table under our profile so we can do some comparisons here. You probably see it already. Notice that the hydrogen lines in our graph match up with the hydrogen lines in the periodic table. There's a red, there's a robin egg blue, some dark blue, and some purple lines. Because of this match, we can now confidently conclude that this gas tube is filled with hydrogen. That's what spectroscopy is all about, matching patterns just like a CSI investigator matches fingerprints. In the next video, we'll determine the composition of stars using these same procedures on your star spectra. But you know what? Lugging around a periodic table and then trying like we just did to find a match in lines, it wouldn't be fun, fast, or accurate. There's a much better way to do it in RSpec. When I click on this toolbar button, this window appears. It has a list of some of the elements. Now watch what happens when I select hydrogen here. Over on the right, see how the profile is now overlaid by a series of vertical blue lines? And look, see how they match the peaks in our data? We found a match to hydrogen, but we didn't need to search that periodic table. Instead of using the table, we can use RSpec to overlay an element template. This makes it much easier. Now, one disclaimer here. In this lab, we're looking at simple examples and doing rough visual matching. If we were doing research, we'd be far more exacting in our processes, and we'd use even more powerful features in RSpec to assure accuracy. As a final step, let's save this profile graph so that we can use it as a reference in the future. I'll click on this archaic floppy icon here, and I'll give the file the name hydrogen gas tube profile graph. Now remember that name because we're going to see it again in the future. So in this video, we've seen how you can use RSpec to process gas tube spectra and identify elements. In the next video, we'll use similar procedures on astronomical spectra.